Now, for section 12.3, we're solving geometric problems with vectors. And the problem with this is we could spend hours on this video or just a few minutes, because, as I said at this end of section 12.2, the point of this chapter is to get you thinking in vectors and to use the information you've got to solve puzzles, really. Now, the thing, what I mean when I say a puzzle is a question that you can't solve with a standard technique. I can't say, look, all the questions you do, this first, this second, this third. You just have to have a general understanding of what's going on, okay? So, what sort of thing can we do? Well, I can run you through these examples, and then from there on in, you're kind of on your own. You've got to use the information you've got and your knowledge of vectors to solve whatever puzzle they put in front of you. So, here we've got 4 points, A, B, C, and D. Now, if this was 2 dimensions, I'd be suggesting you try and sketch these points on the diagram with them roughly in the right place. But here, because it's 3 dimensions, it's difficult to draw any sort of diagram with them in the right place, so we're just going to have to take 4 points. This says find the vector from A to B and D to C. Now that's not too bad, okay? So the vector from one point to another, you just do each of the coordinates take away each other, or if you just like the IJK notation, you can do it like that, okay? So that's reasonable so far. Show that the lines A, B and DC are parallel. Well, to show that they're parallel, you need to show that one vector is a multiple of another, all right? That the vectors go in the same direction. And in this case, they give us the clue as well that DC is 2 lots of AB. So we just need to find the vector from D to C, compare it to the vector from A to B, and show that one is a multiple of the other, and we can do that. So hence describe the quadrilateral. Now this is where we've got to think a little bit. If we've got 4 points A, B, C, and D, and it's told us that D to C and A to B are parallel, so, A, B, C, D, going round the quadrilateral, of course. So D to C and A to B are parallel. Then what are our options in terms of it being quadrilateral? What I could have a square, couldn't I? I could have a rectangle. I could have a parallelogram. Or I could have a trapezium. So it's asking me now, it's saying, well, so what kind of parallelogram is it? And I know that I could have these these are my options. Now, if I've got a square, these two sides are the same length and these angles are right angles. If I've got a rectangle, these two sides are the same length and these angles are right angles as well. If I've got a parallelogram, these two sides are the same length, but these are not right angles. If I've got a trapezium, these two sides are parallel but not the same length. And in what we've just found, it's told us that A, B and A, B and DC are parallel, but they're not the same length. One is longer than the other. Have I drawn that the right way around? Yeah, so DC is 2 lots of AB. So if one is longer than the other, but they're parallel, we must have a trapezium. We can't have these two sides being parallel if these two sides are parallel but different lengths. So it must be a trapezium. So you see the idea, we've known about triangles and trapeziums and parallelograms since at least, I don't know, year 6, but can we apply that knowledge when it comes along in this sort of form, okay? So in example 10 is a really classic sort of thing. We've got 4 points and it says show that they form a parallelogram. So what are we going to have to do to show they form a parallelogram? We know all sorts of things about parallelograms. We know that the opposite sides are the same length, but the angles aren't the same. We know that the opposite sides are parallel. So how are we going to work this out? How are we going to show it's a parallelogram? Well, if we show the opposite sides are parallel, and then we look at the distances and show they're the same length, that should do the job. Do we have to do all of them? Is it enough to get P and S parallel in the same length and Q and R parallel in the same length? Well, if you think about it, that should do the job for us, shouldn't it? Because if that one and that one are parallel and the same length, then these two have to be the same length as well to sort of to make the shape close up. So you can sometimes sort of cut corners a little bit, but make sure that what you've said is going to justify the claims that you're making. The only other thing to point out is if I show that these two opposite sides are parallel and the same length, then how do I know that I haven't got a rectangle? How do I know that I haven't got a square? Well, actually, a rectangle is a parallelogram, isn't it? It's a special kind of parallelogram, and a square is a special kind of rectangle. So possibly, if I don't check the angles, then maybe I've got a rectangle, because maybe these angles here are right angles, but that's fine. If I've got a rectangle, it is a parallelogram. The question's asked me to prove it's a parallelogram, it's not asked me to prove whether or not it's also a rectangle or whether or not it's also a square. So that's enough for example 10. So the only other example, the only other idea here, rather, for section 12.3, the last thing we'll do here is this idea of equating coefficients. And if you remember this, we had a two-dimensional equivalent. But if I have something like this, there is some lots of I, some lots of j, and some lots of k. If that is equal to this vector, then it must have, from the origin, we must have gone 3 in the x direction for this vector here. So we must have gone 3 in the x direction for this vector here. So the coefficient of I on this side must be equal to the coefficient of I on this side. The coefficient of j on this side must be equal to the coefficient of j on this side. And the coefficient of k on this side must be equal to the coefficient of k on this side. Now, that might be easy to see if you write it as column vectors. If this vector is equal to this vector, exactly, not just parallel, but exactly equal, then what we're saying is that these components are the same, these components are the same, and these components are the same. So that's where these three equations come from either way. And that is an idea that works in 2 dimensions, and it's going to work in 3 dimensions as well. Now, I'm afraid that I'm going to duck out of example 12 and leave you to follow that one through on your own, because at this point, you're getting into the idea of, we've used the vectors, you're just going to have to kind of develop that know-how yourself. There's another example there to help you develop that know-how, but there is no new information. The idea of these videos really is to show you the new tactics and and techniques that you can use, which I've already, that I've done everything really on section 12.3. So that's the end of that one. Good luck.